Okay, this is discussion 5.3 on energy cycles. I love energy cycles. I think they're so much fun. I think that once you get them, they really make sense, but this is something that requires a lot of practice and study. So you're going to need to spend some time on this. You can watch this multiple times. You can do homework problems. It's really easy to create your own practice problems for this. So that's something that you can do as well, and we'll do lots of practice in class. All right, so let's jump in. First, what is an energy cycle? So an energy cycle is just an alternate multi-step pathway to determine an enthalpy value. This is the same thing as with Hess's law, where we took multiple equations and added them up to get an overall equation. Then, to get the enthalpy for that equation, we could add all the enthalpies of the equations we added in the first place. Okay? So we're going to look at the following types of energy cycles. We're going to look at enthalpy of combustion and formation, enthalpy of solution, and Born-Haber cycles. So, before we can do the first energy cycle, let's review and learn some terms. First, the standard enthalpy change of formation. So we talked about this in the last discussion, but it is the energy change when 1 mole of a substance is formed from its elements in their standard states. So, remember, if I have an element in its standard state, its enthalpy of formation must be 0, because it already is an element in its standard state, so there's no enthalpy change associated with that process. The standard enthalpy change of combustion is the energy released when 1 mole of a substance is combusted. So, let's say we wanted to create an energy cycle to find the heat of formation for an organic compound. So this could be containing carbon, hydrogen, and/or oxygen. So when organic compounds are formed from their elements, they look like this. All right, so if this was an organic compound with carbon, hydrogen, and oxygen, it would be formed by reacting solid carbon, hydrogen gas, and oxygen gas. Now, this process could be hard to measure directly, okay? So we might not easily be able to get the heat of formation for this process, and we'll talk about some of the reasons why that might be hard to do directly in class. So instead, we could use heats of combustion for carbon, hydrogen, and the hydrocarbon to figure it out. All right, so the way we would do this, if we wanted to go from here to here but couldn't measure it directly, we're going to have to find an alternate route. So we could combust carbon and hydrogen and the hydrocarbon and use their enthalpies of combustion to create a cycle. So, first we'd combust carbon and oxygen. We'll call that process A. Next, combust hydrogen and oxygen. We'll call that process B. And from those two combustions, we'll make CO2 and water vapor. Now, when we combust the hydrocarbon, we're going to make the same thing. So, if we wanted to solve for this process, instead of going directly this direction, we could go around like this. So, the heat of formation could be found by adding the heat of combustion for carbon plus the heat of combustion for hydrogen minus the heat of combustion of the hydrocarbon. Now, you might be wondering why that's subtracted. The reason that's subtracted is that here we're going with the arrow, here we're going against the arrow, so we're reversing the process. So, when you take the reverse of a process, you change the sign. So, let's look at an example of the formation of ethanol from its elements. All right, so first we combust carbon and then hydrogen to make CO2 and water vapor, and then we combust ethanol to complete the cycle. Now, one thing to notice is that this equation was balanced, and it has to be balanced to create 1 mole of this, since that's the definition of heat of formation, so we did use the half coefficient on the oxygen, that's fine. And then, since this is balanced, I also balanced these first two processes going to CO2 and water vapor. And if this is balanced and this is balanced, then this must be balanced, okay? Now, I did write the number of moles of oxygen that react in each step, but if you notice, we add 3.5 moles in this direction, and we're subtracting 3 moles in this direction, so we have overall a half a mole, okay? So it all does cancel out. All right, so the heat of formation for ethanol would be 2 times the heat of combustion of carbon, since we combusted 2 moles of carbon, plus 3 times the heat of combustion of hydrogen, since we combusted 3 moles of hydrogen, minus the heat of combustion of the hydrocarbon. Okay, and we can get these values from table 13 in the data booklet, and when we do the math, we get negative 279 kilojoules per mole. Now, if you're wondering if that's a reasonable answer, you can look at table 12, because it gives you some thermodynamic data. And ethanol is actually included in this table, so we can kind of check our work and see if we're close. So in the data booklet it says negative 278. Now you should not expect your values to exactly match what you see in the data booklet, but they should be pretty close. So we got negative 279, the data booklet says negative 278, so that means that we probably did it right and everything's good. So you might see a general pattern start to emerge as you do more of these problems. So if we're given this equation, X moles of carbon reacting with Y moles of hydrogen and the needed amount of oxygen to produce a hydrocarbon, you'll see that the heat of formation is equal to X times the heat of combustion of the carbon plus Y times the heat of combustion of the hydrogen minus the heat of combustion of the hydrocarbon. All right, so try this problem for the enthalpy of combustion of propanoic acid, using that to find the enthalpy of formation. And pause for a sec, try that, and then check your answer. Okay. So first we write an equation for the process, and this is balanced. Next, we're going to set up the combustions of carbon and hydrogen to produce CO2 and water vapor, and then we'll connect it with the heat of combustion of propanoic acid. And so we can solve 3 times the heat of combustion of carbon plus 3 times the heat of combustion of hydrogen minus the heat of combustion of propanoic acid, and we get negative 513 kilojoules per mole. Now, if we try to check this one in table 12, propanoic acid is not included, but methanoic and ethanoic are, and you see that there's a general trend, and it fits with the trend. So that tells us that our answer is probably correct. Okay, let's do the next energy cycle using enthalpies of solution. All right, so we have to define all the terms associated with this. The first is the standard enthalpy change of solution. And that's a change in energy when I dissolve 1 mole of a substance with excess solvent, typically water. The standard enthalpy change of hydration is a very specific definition. It might not be what you'd expect. It's the energy change when 1 mole of gaseous ions are added to water to form a solution. And finally, we're going to use the lattice enthalpy, which is the enthalpy change when 1 mole of an ionic compound is broken down into gas phase ions. All right, so let's say we wanted to find the enthalpy of solution for sodium chloride. First, we need to write an equation. So we're talking about taking solid sodium chloride and dissolving it in solvent, so we get aqueous sodium chloride. And that's the enthalpy of solution. Now, let's say for some reason we couldn't measure this quantity directly, so we wanted to create a cycle. All right, so we're starting here, and we have to find another pathway to go to aqueous sodium chloride. Now, we have to ask ourselves, what could I do with solid sodium chloride besides dissolve it in water? Well, I could use the lattice enthalpy and go to gas phase ions. All right, so that's the first step. And then once I have gas phase ions, I can connect those to the aqueous solution using the enthalpies of hydration. Now note that these are for each ion. So when you look in the data booklet to get this information, you'll find 1 value for sodium and 1 value for chloride. So we're trying to do this process. So the enthalpy of solution is equal to the lattice enthalpy plus the enthalpy of hydration for each ion. So we'd get 790 plus negative 424 and negative 359. Now, enthalpy of solution is probably the easiest of these to find experimentally. So if we wanted to create an energy cycle to find the lattice enthalpy, for example, instead of doing this directly, we could take the enthalpy of solution minus the enthalpies of hydration. If we wanted to find the enthalpy of hydration, we could go backwards around this way. So we could do the negative lattice enthalpy plus the enthalpy of solution. So these energy cycles are really versatile. You can use them to find any quantity you want. Just start at your starting point and go to your ending point. If you go against the arrow, subtract. If you go with the arrow, add. Okay, and the final answer you get here is 7 kilojoules per mole. Now all of this data is in tables 18 through 20 in the data booklet. So 18 is the lattice enthalpy, 19 is enthalpy of solution, and 20 is enthalpy of hydration. So sodium chloride is actually given in table 19 with the enthalpy of solution, and it's given as 3.88. So again, it's not exactly the same, but we can kind of see that we're in the right ballpark. So our answer is correct. So try this problem for the enthalpy change of calcium chloride. Note, since there's 2 chloride ions involved here, you're going to have to take that into account with the enthalpy of hydration. Okay, so pause for a sec, try this, and then check your work. Okay. First, write an equation, and that's our enthalpy of solution. Next, write an equation for the lattice enthalpy, and finally for the enthalpy of hydration. So the enthalpy of solution is the lattice enthalpy plus the enthalpy of hydration for each ion, and since we have 2 chloride ions, we're going to have to multiply that enthalpy value by 2. And so our final answer is negative 63 kilojoules per mole. This is actually not in table 19, so we can't compare, so we just have to be extra careful and make sure that we're doing things correctly. Okay, let's talk about our last cycle, Born-Haber cycles. Now, these initially seem like they have a lot of steps, and there's a lot to memorize, but I want you as much as possible to try not to memorize steps, but to think through all of the processes. So try to think through it, not memorize through it. I know that can be hard to do and it's tempting to memorize, but try. All right, so we use Born-Haber cycles to calculate the heat of formation of an ionic compound. So for example, we could find the heat of formation of lithium fluoride from lithium and fluorine gas. And the question is, how could we create an alternate pathway to get from solid lithium and fluorine gas to solid lithium fluoride? So if we could get from the solid lithium and the fluorine molecules to gas phase ions, we could use the lattice enthalpy to connect back to the lithium fluoride. All right, so let's think about the steps that would be involved in this. For the metal, first we need to use the enthalpy of atomization or sublimation. So this is taking our solid lithium and making it into a gas. This is not in the data booklet, so it either has to be provided in the problem or it could be the quantity that you're solving for in the problem. Next, once we have a gas phase metal atom, we're going to use the ionization energy to create an ion. Okay, remember ionization energy is the amount of energy required to remove an electron from an atom, so since metals lose electrons, this is what we need to use. This is in table 8 in the data booklet. Now notice, it's really important, we have to, technically for our cycle to be correct, we have to do the enthalpy of sublimation first, because ionization energy is defined in the gas phase. Okay, so then we have our gas phase metal ion, and then we have to look at the nonmetal. And for the nonmetal, first, most of these are going to be diatomics, so we have to use the bond enthalpy to separate the molecule into atoms. And that's in table 11 in the data booklet. And then we have to use electron affinity. So that's the enthalpy change when an atom gains an electron or electrons. And that's in table 8 in the data booklet. The signs associated with each step, it's helpful to know these when you create your cycle. Enthalpy of atomization is positive because energy is required to go from a solid to a gas. Ionization energy is positive because energy is required to remove an electron from an atom. And for the nonmetal, bond enthalpy is positive because energy is required to break bonds. And electron affinity is negative for the first electron, but the second can be positive. All right, so when we create this cycle, we're going to start by writing our heat of formation process. Now, notice that I have it going downwards. That's because we're sort of creating a cycle so that energy is like the y-axis, I guess. So we're trying to show the relative energy involved in each step. So if the sign is positive, we'll go upwards. If the sign is negative, we'll go downwards. And since we know that this should be an exothermic process, we're going to write it going downwards. All right, so let's look at all those steps. First, the enthalpy of atomization of lithium, so going from solid to gaseous lithium, and that's 159 kilojoules per mole. Again, that have to be given to you. Next, we're going to use the ionization energy of lithium, and that's 520 kilojoules per mole from table 8 in the data booklet. Okay, so lithium is a gas phase ion. That's ready to go. Now we have to make fluorine into gas phase ions. Okay, so first, we're going to use the bond enthalpy. Now, we're only going to use half the bond enthalpy value for fluorine because we're only separating half a mole of fluorine. Now, when we separate half a mole of F2, we're going to have a whole mole of fluorine atoms. Next, we'll use the electron affinity of fluorine, and now we have gas phase ions. All right? Now, we're going to connect these using the lattice enthalpy. Note that the lattice enthalpy goes in this direction since it's breaking down solid lithium fluoride into gas phase ions. And that, again, is in the data booklet in table 18. So, if we want to solve for this quantity, we're going to go all the way around this way. If we go with the arrow, we add the value. If we go against the arrow, we subtract it. So we take 159 plus 520 plus 1/2 times 159 minus 328, or plus negative 328 minus 1049, and we get negative 618.5 kilojoules per mole. Okay, so try to create an energy cycle to find the heat of formation for calcium chloride, given that the enthalpy of atomization of calcium is 178 kilojoules per mole, and the second ionization energy of calcium, since it loses 2 electrons, is 1,145 kilojoules per mole. So pause for a second and then check your work. Okay, so we're going to start the same way we did before, writing the equation for our heat of formation. First, we're going to do enthalpy of atomization of calcium. And then we're going to do the first and second ionization energies for calcium. The first you can get, again, from the data booklet. Now we're going to use the bond enthalpy for chlorine, and we're separating an entire mole of chlorine molecules, so we're going to use just the value as it's written. Now we're going to use 2 times the electron affinity of chlorine because we have 2 moles of chlorine atoms gaining electrons, and finally we'll connect it with the lattice enthalpy. Okay, so to find the heat of formation, we're going all the way around in this direction. So we'd have 178 plus 590 plus 1,145 plus 242 plus 2 times negative 349 minus 2,271. Okay? Now, if you wanted to solve for this value, instead of going directly here, you'd go all the way around here. Okay? So you'd take the heat of formation plus the lattice enthalpy minus the electron affinities minus the bond enthalpies minus the ionization energy. Okay, so this is, again, really versatile. You can use it in a lot of different ways. Okay, go practice, ask lots of questions, and good luck.